Welcome to this presentation. And in this presentation, I introduce the state space representation of control systems. So we look at state space representation, the state space representation of control systems. Basically, we define state space representation or state space approach as a time domain method of modeling, analyzing, and designing control systems. So in other words, we can use the state space approach to model, to analyze, and to design control systems. So our first section will deal with the modeling of control system in state space approach. For us to design systems in state space approach or state space representation, we require knowledge of three variables. The first two have been defined previously in previous studies of control system. One is what we call the input variables. Input variables basically represents the excitations to the system, the control system. Number two, we need the output variables. We need the output variables. The output variables represent the responses to the control systems. And then number three, we require what we call the state variables. State variables will be defined as those variables such that the knowledge of these variables at t equals to t naught. T naught indicates the origin of the state space. So the knowledge of these variables at any time t equals to t naught plus the knowledge of the inputs, at t greater than or equal to t naught will help us determine the response of the system completely. So if we know the variables at t is equals to t naught, the inputs at t equals to or greater than t naught, those variables will help us determine the response of the system, and such variables we define them as the state variables for any given system. For purposes of our discussion, we will use u of t to indicate the input variables or to denote the input variables, y of t to denote the output variables, and x of t to denote the state variables. Now, any given system can be modeled mathematically using differential equation, and at the end of the day, depending on the order of the system, we can have an nth order differential equation that represents that given system. The solution of the responses to the system using the nth order differential equation becomes tedious, and therefore we attempt to break down the nth order differential equations into n first order differential equations. So if we can break down the nth order differential equation into n first order differential equation, we come up with two sets of equations. One we call the state equation, and number two, what we call the output equation. These two equations represent what we call the state space model of the system. So basically, we'll be taking an nth order differential equation, break it down into nth order first order differential equation from which form a state equation and an output equation, and the two will constitute what we call the state space model of a control system. Any given system, any given control system can be represented in terms of its state equation and the output equation in standard form as follows. So the state equation will involve the derivatives of the states as x prime of t, or x derivative of t, is a function f of the states, the inputs, and time. And the output of the system is a function g of the states, the inputs, and time. You can call this equation 1 and call this equation 2. So this is what we call the state equation, and this is the output equation. For our study, we restrict ourselves to linear time invariant systems, linear time invariant systems. For linear time invariant systems, equations 1 and 2 can be written as x derivative of t is equals to a x of t plus b u of t, and y of t is equals to c x of t plus d u of t, where a, b, c, and d are constant matrices. These are constant matrices. So we'll be able to define any linear time invariant system using the two equations where a, b, c, and d are constant matrices. The state equation and output equation, denoted by equations 3, you can call this equation 3 and this equation 4, can be modeled in block diagram representation to represent the system modeled in state space as a block diagram as follows. So if we are to model the system in block diagram representation using the state equation and the output equation for a linear time invariant system. So if I start with the first equation, the state equation, the input goes through a block B. So this part goes through a block B. So this is our input u of t. From there, we have that being summed. So we have a summing point, and the summing point is taking in a content x of t having passed through a block A. So we can have a block A, and therefore this content is x of t. Then when you sum the two, you get x derivative of t. And you notice x of t is being generated from x of t derivative, and that means this block must be an integrator, so that when we integrate x derivative of t, we get of x of t, we tap it for feedback, and that models the first equation or the state equation. Then the output equation y of t is cx of t plus du of t. So at this point, we have our x of t. We pass it through a block whose content is the matrix C. And then after that, we have a summing point, another summing point, And to that summing point, we are adding the contents of Cx of t and du of t. That means we tap u, pass it through a block whose content is d, and through into our summing point. And out of that summing point, we get our y of t. So this becomes the block diagram representation of a system modeled in state space approach. Next, we consider determination of the state space model of any given system given the differential equation or the nth order differential equation that governs the operation of the control system. I'll handle this in terms of, or illustrate this in terms of an example. Suppose we have a system defined by the differential equation, a system defined by the differential equation d cubed of y dt cubed plus 6 d squared y dt squared plus 11 dy dt plus 6y is equals to 6u. It's good to note that when I write y, I basically mean y of t, and when I write u, it represents u of t. So this is the differential equation of a third order system, being a third order differential equation that models an third order system. We are to obtain the state space representation of the system from the differential equation. If we were to solve the differential equation, we would need the knowledge of y of 0, y prime of 0, and y double prime of 0. These are the initial conditions that we need for us to be able to obtain the solution of the differential equation. In that case, then, we can choose the state variables as follows. So we take the first state variable, x1 of t, we take it to be equal to y, and x2 of t is y prime. So to indicate all the initial conditions that we require, and then x3 of t to be equal to y double prime. From these state variables, x1, x2, and x3, which are dependent upon the initial conditions that we require so as to obtain the solution of the differential equation as y0, y naught 0, and y double naught 0, then we can obtain the first derivatives of the states as follows. x1 derivative is equal to y derivative. From this, we notice that x1 derivative is y derivative, but y derivative is x2. Then x2 derivative will be equal to, differentiate x2, you have to differentiate y derivative, which will be equal to y double derivative, but y double derivative is equal to x3. Finally, x3 derivative is equal to y, that derivative. From here, differentiate x of 3, you have to differentiate y double derivative, that gives that derivative, which will be equal to, then from this equation, we can write our that derivative by taking all the terms to the right And notice that we'll get this as minus 6y minus 11y derivative minus 6y double derivative plus 6u, which is equals to, so from this, our minus 6y, y is x1, so we can write this as negative 6x1, negative 6x1 minus 11, y prime is x2, so 11x2 minus 6 double prime of y, which is x3, and then plus 6u. So this is the set of the first order simultaneous equation as the derivatives of the states. Finally, we can write the output y of t to be equal to, so y of t is x1 of t, and of course the values of x2, x3, and u are 0, so you can write this as 0 x2 plus 0 x3 plus 0 u. Using this set of equations, we can obtain the state space representation of the system as follows. The state equation will involve the vector x1 derivative, x2 derivative, and x3 derivative as a vector, which will be equal to a matrix A, or matrix A, multiplied by the state vector x1, x2, and x3. Plus a matrix multiplied by the vector u of t. Remember, we want to write this as x derivative is ax plus bu. So x denotes this vector, u denotes this vector, a and b are our two matrices, and then x derivative denotes this vector. So we start with x1 derivative is only a function of x2, that means 0 for x1, 0 for x1, 2, 1 for x2, and 0 for x3. Doesn't have an input, and therefore 0 for u of t. x2 derivative is equal to x3, which means a function of only x3. That means 0 for x1, 0 for x2, and 1 for x3. It is also not a function of u, and therefore 0 for u of t. Finally, our x3 derivative is negative 6x1, so we have negative 6, negative 11x2, so negative 11, and negative 6x3, negative 6x3, plus 6u, and therefore its u value is a 6. And this is our state equation. Next, we can write the output equation. The output equation in matrix notation as follows. Our y of t can be written as a matrix C multiplied by the state x1, x2, x3 plus a matrix multiplied by u. So in this case, y of t is x1, 0x2, 0x3. That means 1 for x1, 0 for x2, and 0 for x3, and then 0 for our U, and this becomes the output equation where the matrix C is 1, 0, 0, and the matrix D is equals to 0. And this is the state space representation of the system defined by the differential equation, which was a third order differential equation. This is the process of determination of the state space model given the nth order differential equation. In my next study, I discuss determination of state space model for electrical circuits. Thank you so much.